Okay, guys, so first video, well, officially the last lesson that we have to talk about. We're going to be talking about the idea of transforming um, to achieve linearity. So we may have some relationships that um, don't appear to be linear, but we'll kind of manipulate a few things in our data in order to transform them to become more linear so that we can find a regression line which can help us for predicting um, other values. So in Unit 3, we learned how to analyze relationships between two quantitative variables that showed a linear pattern. When two variable data show a curved relationship, we must develop new techniques for finding an appropriate model. This section describes several simple transformations of data that can straighten a nonlinear pattern. Once the data have been transformed to achieve linearity, we can use least squares regression to generate a useful model for making predictions. And if the conditions for regression inference are met, we can estimate or test a claim about the slope of the population regression line using the transformed data. So applying a function such as logarithm or square root to a quantitative variable is called transforming the data. We will see in this section that understanding how simple functions work help us choose and use transformations to straighten nonlinear patterns. Okay, so Gapminder website provides loads of data on health and well-being of world's inhabitants. Below is a scatter plot of the data from Gapminder. The individuals are all the world's nations for which data are available. The explanatory variable is a measure of how rich a company is, referring to income per person, versus the response variable, which is life expectancy at birth. So we would expect people in richer countries to live longer just based on they would have more access to better medical care. The environment they live in is healthier. They typically probably lead more healthier lives. Um, and so this scatter plot would show that. But the pattern in the scatter plot shows this, but it's a curved pattern. It's not a linear pattern, which means we wouldn't be able to find a regression line to kind of predict a value. So life expectancy rises very quickly as income per person increases. Then it kind of levels off a bit. So that there would suggest that it's not a linear relationship, but more of an exponential or power relationship. So we can straighten things out by using logarithms. So the figure below plots the logarithms of income per person against life expectancy for the same countries. So this would be a plot of the logarithm of income per person against the life expectancy. The graph now has a much more clear and linear pattern. So from this scatter plot, we would be able to find a least squares regression line and then use it to predict or test certain claims about it. So applying a function such as a logarithm, or we'll see a square root, to a quantitative variable is called transforming the data. Okay, so when you visit a pizza parlor, you order a pizza by its diameter, say 10 inches, 12 inches, or 14 inches, although it's usually like small, medium, or large. But the amount you get to eat depends on the area of the pizza. The area of the pizza is pi times the square of its radius, r. So the area of a round pizza with diameter x is as follows. And you could see that this would be a power model. And the power model would fit the form y equals ax to the p power, where a would equal the pi over 4 and p would equal 2. So although a power model of the form y equals ax to the p describes the relationship between x and y in this setting, there is a linear relationship between x to the p and y. So maybe not a linear relationship between x and y, but there would be between x to the p and y. So if we were to transform the values of the explanatory variable x by raising them to the power p, graph the points x to the p, y, your scatter plot would now have a linear form. So similar to that was this. So instead of plotting your income per person versus your life expectancy, so your income per person being your x and your life expectancy being y, we would now have, this would be your normal x, this would be y. We wouldn't want to plot xy to achieve linearity, but instead we'd want to do the log of your x's and y, and that shows a linear relationship. And then we would see our curves pattern straighten out. Okay, so I'm gonna kind of piece together things a little bit at a time. So it may seem very easy at first, but then it starts to get jumbled. So feel, more than free to write down questions and ask me in class. So first example, go fish, and we'll refer to this a few times. Imagine that you have been put in charge of organizing a fishing tournament in which prizes will be given for the heaviest Atlantic Ocean rockfish caught. You know that many of the fish caught during the tournament will be measured and released. You are also aware that using delicate scales to try to weigh a fish that is flopping around in a moving boat will probably not yield very accurate results. It would be much easier to measure the length of the fish while on the boat. What you need is a way to convert the length of the fish to its weight. So reference data, the data table is coming from, it was provided by a marine research lab, so just research that had previously been done. So the reference data on length in centimeters and weight in grams for Atlantic rockfish of several sizes is plotted. Note that we see a clear curved pattern. So because length would be one-dimensional and your weight is three-dimensional, like volume, think of volume being like weight. So because weight would be more three-dimensional, we could use, a power model of the form weight equals a times length to the third power should describe the relationship. So this transformation of the explanatory variable, taking the length and raising it to the third power, would help us produce a graph that is linear. So that transformation would work. Another way to transform the data to achieve linearity is to take the cube root. It's basically the same thing, but you're doing the opposite. So it's to take the cube root of the weight values and graph the cube root of weight versus length. So now you're talking about cubing the weight and leaving the length. So you're just doing the opposite. Once we straighten out, but again, you would also see that this would straighten out your curve up here. So once we straighten out the curved pattern in the original scatter plot, we fit a least squares regression line to the transformed data. This linear model can be used to predict values in the response model. So now what we can do is, if I give you the mini tab here, we could give the equation of the least squares regression line, and we're going to define any variables we use. So transformation 1, where we took the third power, or took the length to the third power rather, would look like as follows. So remember that this would be transformation 1. So here, why is this not working? Okay, so here would be your, as always, your slope. Same thing in this one. This, I'm sorry, y-intercept, and then this would be your slope. Okay, where in the second one, this is your slope, but it's always the same in your mini tab output. The big difference here is, are you raising the length to the third power, or are you taking the cube root of your weight? So now, it doesn't go away. So now, suppose a contestant in the fishing tournament catches an Atlantic Ocean rockfish that's 36 centimeters long. Use the model from part A to predict the fish's weight. Show your work. So in transformation 1, just ignore the pen because I don't know why it's there. So 36 to the third power, as opposed to plugging in 36 and then taking your answer and then raising that to the third power, because that would be what your cubed root would equal. Why can't I reset it? No. Okay. So we're going to leave that off. Okay. So that should be it for our first video.